Okay, thank you very much for the introduction. Can you hear me? Is this working? Okay. I cannot hear anything, so, or nothing amplified. So this is a big honor and pressure to be the first speaker at the conference. So I'm going to make it an introductory talk into applications of set theory. That's how the name of the workshop got stuck in my memory. I didn't remember the complicated name, but I thought it sounded like applications of set theory. And since then, I am calling myself an applied set theorist. So I hope that's going to help with grant application and these sort of things. So these are going to be connections between Ramsey theory and topological dynamics, and I'll try to convince you that there is some set theoretic connection. And even though we might not be using very difficult set theory, maybe the notions from set theory may be useful, or the set theoretic point of view that many mathematicians are sort of boycotting. I talked about some of these aspects already at the workshop in Norwich, so I will not be talking about those, not to bore those that have been there and of course remember everything. So I will not talk about ultrafilters and their connection, but it is implicitly in there as well. So why do we care about Ramsey theory? I hope that everybody can find some reason in there. For instance, Stevo wrote a book about it, so it must be interesting. But there is, it's a combinatorial phenomena that in one form or another appears just about everywhere. We sometimes run into that, we want to solve it, and often we find it quite annoying because it's something that we know it's true, or well, sometimes it's quite unbelievable, but sometimes this is the thing we want and it's difficult to prove. And I would like to give you a hope that maybe we can use topological dynamics to do something like that. But there is an inspirational question by Gromov in his new book, which is not really published. I can see that. As I was saying to Joan, I forgot my charger in New York, and this looks like a little different version than I thought it was. So this is the question by Gromov, who is asking whether behind all these Ramsey theoretic phenomena, and he has definitely in mind geometry as well as combinatorics and ergodic theory, can we find some invisible structure behind them? And where I am looking for them is in topological dynamics and representation of topological groups as groups of automorphisms of structures in whichever logic you choose. So this is one of the nice motivations. So let me phrase what the original Ramsey theorem is, or what we call the Ramsey's theorem that was used to prove some classification result for binary relations, and it was just a small lemma that turned out to be very useful in many places. So we always, in these sort of Ramsey type statements, start with some small structure, so in this case just an integer k and a larger integer m and the number of colors. So not to be trivial, we want it to be at least 2. And then we are looking for some Ramsey solution, that means some large number n, such that no matter how we color copies of the small structure, so here just k element subsets of the large set in 2 colors, or are many colors, then there exists a copy of the medium structure, so here there is a copy of size m, such that all the smaller structures inside have the same color. So this is the exact statement. But we can already state this Ramsey theorem in many different forms. So for instance, we can phrase it in terms of linear orders. We are looking at subsets, so we can as well just order them, because we are not looking at their permutations. So we can rephrase that as saying that if we take a k element linear order and an m element linear order and a number of colors, then there exists a large linear order such that if I color all small suborders by finite number of colors, there exists a medium size suborder that is monochromatic on k element suborders. Or we can phrase that in simplices, so we can say that we are coloring k-dimensional faces of some large simplex, and we are looking for a monochromatic m-dimensional face. Okay, so this is the original Ramsey statement already placed in different settings. So what is the Ramsey property? I'm really afraid what's going to happen with these slides, because this is really not the version I have in my email, so you might have to go there. So a class of finite structures satisfies the Ramsey property if we now think of these, instead of just sets, as arbitrary structures in a first-order language. For now, we will go into other languages. So we have a small structure and a medium structure and a number of colors, and we are looking for a large structure such that no matter how we color copies or embeddings, but let's make it easier for copies, of the small structure in the large one, there is a copy of the medium structure inside of the large one, such that all the small copies have the same color. So, examples. As we said, finite linear orders just by Ramsey's theorem, or finite linear order graph, graphs Nishitril and Rödl. This was start of the structure of Ramsey's theory, and many results came after. Or match newer result that was inspired by the Eurizon space and its isometry group, finite linearly ordered metric spaces, proved by Nishitril in 2005, or what we call the dual Ramsey theorem, which is about Boolean algebras, so finite Boolean algebras by Graham and Rochelle. I will mention that one later on, but basically, as we were looking here at embeddings, we are just reversing the arrows, and that's why the dual comes in. Okay, so let's see how Ramsey connects to high symmetry. So this is the connection between model theoretic properties and the Ramsey property. So let's start with a class of finite rigid structures. Rigidity just means that we have only the trivial automorphisms. And if you have a class that is hereditary, meaning that if I have some structure in a class and I have a substructure, then also the substructure is in there. Joint embedding property, meaning that if I have two structures in my class, then there is a large structure that embeds them both. And if, moreover, the class satisfies the Ramsey property, then it also satisfies the amalgamation property. We can glue things together along a common core. So if we have two structures that are intersecting somewhere, or two embeddings from the same structure, then there exists an ambient structure that embeds both of them with respect to this. So that allows us to build larger and larger objects in our class. And this is exactly what was not supposed to happen. I'm sorry, the file just got copied, but I'm afraid it didn't replace the old copy. Can I do something terrible and open it from my email? I'm very sorry about that. As I said, I looked at it on my phone where I downloaded things from my Gmail. And as I didn't have the computer with me, I'm very sorry about it. I wouldn't mind. I think that you are all smart enough to actually get there without me giving it to you. So I think it's easier for many of you to make it happen rather than remembering it, right? Well, I hope that's some entertainment. And let's see, okay, now the clicker is not working with a version that's straight from email, I suppose. But we are getting there. So, now this is where we were. So now we are at the, what I meant by high symmetry. So by high symmetry, I mean structures that are very homogeneous. In this case, for structures of automorphisms, I mean that if I have two substructures that look the same, that means that there is a partial isomorphism, then I can extend to the whole automorphism.
Question? Mm-hmm. I thought that that K was supposed to be rigid structures.
That was on the previous slide to ensure that we do have the amalgamation property from there, because it's this part works only if you have rigidity, otherwise you would have to be talking about embeddings. So but Frey's theory works for everything. So Ramsey property implies amalgamation property in case of rigid structures. And it's of course not vice versa. Of course, amalgamation property is not equivalent to Ramsey property. Ramsey property is something that is more difficult to achieve. Okay. So, but ultra homogeneity we get from the other properties. It is what I want to say is that if we already have Ramsey, which is more difficult thing, we do not have to show amalgamation property, which is often annoying to prove. But that also makes the philosophical connection between high symmetry and Ramsey, that often these two things come together, and this would be the reason for that. So by an old standard theorem of Price, if we have hereditary property, joint embedding property, and the amalgamation property, then we can glue all the pieces together to get a countable structure that has this high homogeneity, ultra homogeneity property. Okay. And vice versa. If I take a highly homogeneous structure and I take all finitely generated substructures, then these structures, these classes are going to satisfy these three properties. So this means that we can be looking at these countable structures by the finitely generated approximations. I will be looking at structures that are locally finite so that I can talk about finite substructures. Locally finite means that finitely generated substructures are finite, but most of the theorems are true even when we go to finitely generated. More questions? Okay, so now we go from these finite approximations to see how groups of automorphisms of these highly homogeneous structures are related to that combinatorics. So we start with a first order structure, and we are looking at the group of automorphisms with a pointwise convergence topology. There is a nice description of a basis of neighborhoods of the identity. We take some finitely generated substructure, and we take pointwise stabilizer of that substructure, and this is a Clopen subgroup. So these groups, in a way, are close to discrete groups because we have these coset spaces to work with, but there is very, very big differences in the dynamics. And let us know that if my large structure is ultra homogeneous, then I can relate cosets of a pointwise stabilizer of a structure with embeddings of the small structure in the large structure. For instance, if I have some coset GAG, this is going to correspond to an embedding that is given by G inverse of A. So this would be going from G inverse of A inside of A, if I have A somewhere given, right? So I have one A fixed as a substructure, and then I'm looking at all the other ones, and because I have ultra homogeneity, embeddings are exactly the same as cosets of the stabilizers. So this is the transition why we can be talking about the automorphism group from the point of view of the substructures of the structure. Okay, and now let's make a connection with some infinitary property on the structure and covers of the group. So we will be always talking about ultra homogeneous structures because every group of automorphisms can be represented as a group of automorphisms of an ultra homogeneous structure. So we are not losing any of the groups, and we can be using this connection, and we have its group of automorphisms and finite substructures. And we can now be talking about A being a Ramsey object and not looking for the solution, this large C, but we can be actually coloring directly copies of the big A. So before that, we had that K was a Ramsey class if every A was a Ramsey object, meaning that for every B and every number of colors there existed a large C. We can actually use a simple ultrafilter argument to say that this is the same as coloring copies of the small structure in the infinite structure, in the big ultra homogeneous structure, and we will be finding arbitrary large structure from our class finite substructure that will be monochromatic, and we can actually achieve this to be in the same color always. And how does that relate to some global property of the group? So we can phrase that in terms of these coset space. So if we make a partition of the coset space into finitely many pieces, that means we are coloring the cosets, then there is going to be one piece that as a subset of the group, so this GAKI is going to be thick. So this is one notion of largeness in topological dynamics. It means that, well, this is one way to define it. I always find it nice to define things in as many ways as possible to get a feeling of it. So an equivalent way would be that if we look at all the translations by elements of our group F, then this has the finite intersection property.
Did you mean for F and F?
No, this is all of them. So this is the same as saying this. Let me put a different letter so that it's not confusing. This F would be some finite subset that is, and this X is going to witness something in the intersection. This X is going to be inside of F inverse of GAKI for every F inside of F. So this is the equivalence between the two definitions. And let me maybe show why this is equivalent to the Ramsey property. So because we are talking about Ramsey property for substructures and not for embeddings, let me assume again that the H of A consists of rigid structures. And in this case, we not only have that the coset space corresponds to embeddings, but it exactly corresponds to copies of a small a inside of A. Now, if we have the partition of G into finitely many unions of cosets, then this is the same thing, therefore, as a coloring from copies of A into R many colors. Right? Now, to show that from Ramsey property we get the thickness, it is enough to consider the B prime that is, sorry, let me start with the F subset of G finite. This is the thing we are looking at, and now we look at images of A under these guys, and we generate a substructure of A. And now by the Ramsey property, we know that there is a copy of B prime that is monochromatic. And now, by ultra-homogeneity, we know that there is going to be a mapping that is, and now let me check the sides, where we are going from to where, from B prime to B. And this is going to witness the symplecticity. So we will have that in color I. Then we get that GAFX is a subset of GAKI. So remember that here we had one A fixed, and the copies were given by G A, G inverse of A. So it's a very simple connection, but it gives us tools how to use other methods. These methods have been so far developed only for groups that are discrete, but we are working on them in groups of automorphisms. And this was the definition that Andreas was using to say that a subgroup of a group is Ramsey in this subgroup is Ramsey in here. And he was asking a very interesting question that I don't know if there is an answer to that yet completely. If I have 3 groups. So if I have, it would be very useful, it would be very beautiful if this was true. So take this definition of thickness for arbitrary group that we replace this GA by, and we have K subgroup H in here, and H is Ramsey in G. So if we take any partition of cosets by H into finitely many pieces, one of them is thick, and the same is true for K inside of H, that these are Ramsey. The question is whether K is Ramsey inside of G. This would be a very powerful statement, and hopefully this can be proved in some generality. So this is what I learned in the last workshop, and this is one motivation why to look at this definition as well. Any questions? So this is the connection to infinite theory combinatorics in here. And for instance, very easily we get from there without any work that if we have a larger substructure D and a smaller substructure A, and the smaller substructure is a Ramsey object, then so is the larger one. So this is something that one would have to think about in just the finitary language, and here it comes out for free. And with an ultrafilter viewpoint of dynamics, this theorem comes out for free as well these days without work. But when it came out first time, this is a big breakthrough connecting the dynamics and the Ramsey theory by Kekris, Pestov, and Todorčević. So again, we start with ultra-homogeneous structures so that we can connect the topology and the finite substructures. And on one side, we have the combinatorics. So we have the Ramsey property, and we do have rigidity. Rigidity is necessary not to have any movement in item 1, which is that the group has a fixed point under every continuous action on a compact Hausdorff space. So this definition is going to appear on the next slide. But what does it mean? So whenever we are acting on a compact Hausdorff space, so we have a continuous mapping jointly on the product, such that the multiplication works as composition of homeomorphisms and identity is just identity. This is saying that this group has always a joint fixed point. So this is a very strong fixed point property, meaning that there exists x in x, such that gx is equal to x for every g in g. Right? So often we hear in analysis we are looking for at one mapping and one space and one action, and we are looking for one fixed point. Here we get a fixed point for all of the mappings at the same time. We call that extreme amenability. So this was big on the side of dynamics because it was not known how common these groups are, the extremely amenable groups, and it was believed that they are pathological. They are basically things that should not appear. They appear only in weird cases. And it was Bill who asked for their existence at first time. At least that's what we refer to now. And now we know that it's exactly as common as the Ramsey property. So that's something that we still do not really know how common it is. But we definitely have some natural examples. So for instance, we saw that finite linear orders have the Ramsey property, and this large homogeneous structure countable that is related to that is group of is Q as a linear order, and from this theorem we immediately get that the group of automorphisms preserving the order is extremely amenable, has this strong fixed point property. And whichever example we had of rigid structure, so also if we take the random ordered graph, this conclusion is going to be the same, so we can plug things in. So let me now go into the dynamics side, where we can say more than only just identifying those groups that always have fixed point. So I will call continuous actions flows. So let me just remind that we are only acting at compact Hausdorff spaces. There's a whole other dynamics where the spaces do not have to be compact, and some of the things are general, some of those things are specific, but compact are really nice. And we often study flows that are minimal, so that means that there is no smaller invariant closed subset. We can also express that in orbit language, meaning that whatever point we take and we look at the orbit is going to be dense in the space. And among all minimal flows, there is one special one that is the largest one. I wonder if I ever will give a talk that there will be no universal minimal flow mentioned. It's a start. So the largest one is called the universal minimal flow. So of course it's given with a specific action, and it has the universality property with respect to all other minimal flows, meaning that there is a morphism, there is a continuous mapping from it onto any other minimal flow, such that it respects the action. And well, for extremely amenable groups, the universal minimal flow is going to be just a fixed point, just that one fixed point or any of them. So it's going to be just a singleton, right? Because if I have a fixed point, then this is definitely invariant under the group action, and there is nothing smaller than that. That is non-trivial. So, but we can say more. So if we have, for groups of automorphisms of countable structures, Kechristov-Todorčević also built a machinery how to compute universal minimal flows if we have some Ramsey inside. And in the end, the description goes by expansions of my structure. So I start with a structure A in a language L that is ultra-homogeneous. And I'm looking at a larger structure, not larger, in a larger language. That is also going to be ultra-homogeneous, and it will really be the structure that extends. So we have that if we restrict to the original language, we do get A, and this structure will, the finite substructure will have the Ramsey property. They will be rigid, so the group is going to be extremely amenable, and it is also going to be large. So the quotient of the original group by the group that stabilizes all the expansions that we put on it is going to be pre-compact, and the completion is the universal minimal flow. So this is what they are getting in there. And these are examples or where this was applied. So before the large paper by Kechristov-Todorčević, there was a result by Glasner and Weiss, where they computed the universal minimal flow for S infinity, the group of all permutations on natural numbers, and they identified that the space is all linear orders on n. And what they used was the Ramsey theorem. All finite substructures of n are just finite structures. They do have the Ramsey property, but they are not rigid. If you put linear orders on them, they are going to be rigid. So in this case, what we get, we have n. Well, we can also think of that as Q. And then the extended structure is going to be just the dense linear order, and then the universal minimal flow is going to be, well, S infinity, which this is just a set, so we can think of that as all Q with no structure, modulo the order-preserving automorphisms, and the completion, and this is all linear orders on, let's say, Q. Okay, so this is one example. Then also the paper about the Cantor space came before Kechristov-Todorčević, again by Glasner and Weiss, but it was treated as a special thing, again, and there they used the dual Ramsey theorem. So Cantor space can be viewed as the countable-bottomless Boolean algebra. It's algebra of closed sets, and we saw that the class of finite Boolean algebras does have the Ramsey property, but again, it's not rigid, so we have to put some linear orders. And in the topological language, if we look at the limit, these orders correspond to maximal chains of closed subsets. So I think this is nicer description in that language, but the core was the dual Ramsey theorem in there. So again, expanding the structure. And then for a random graph, we put linear orders, we get again Ramsey class, so they're all the orders, the same thing for hypergraph in a given language, so language has to stay the same. And or finite fields, vector spaces, infinite vector space over the finite fields, so finite vector spaces, they are a Ramsey class by Graham, Leib, and Rothschild. We again have to rigidify. So this gives us a bunch of examples. We were working with Ola Kwiatkowska and the Lelek fan, which is a little special case. We do first work on a group of automorphisms, but from there we go to a group of homeomorphisms of this one-dimensional continuum. So this is an extended use even outside of just structures that are discrete. I will say a little bit more about that later. But let's see how we can express that in Ramsey. So see here that we were looking at A and some extended structures. So we were putting more relations typically on our class. Well, what does that mean in terms of the original structure? When can we put more relations such that we are going to get everything? That means we will get a homogeneous structure, we will get Ramsey property, and we also will get the quotient precompact. This is what we need to preserve. We otherwise getting Ramsey, we can always do. So now this is about not Ramsey objects, that means degree 1, but possibly having more colors that we have to include, but we can bound them. So before that we could always find a place where all those structures look the same. Now they might not look the same, but there is finitely many types that we can recognize. So what does it mean? A structure, finite structure, has a Ramsey degree smaller or equal to than some integer t in the class, so it's always with respect to the class, if for every larger structure in every number of colors there is a copy of the medium structure such that the small structures take on at most that number of colors. So R can change, R can be as big as possible or as you want, finite, but you can always bound yourself. And this characterizes when the flows are small, and this is exactly when they can be characterized in this way. So Kechristov Todorchevich in one direction and Andy Zucker in the other direction using ultrafilters showed that the universal minimum flow of a group of automorphisms of an ultra-homogeneous structure is metrizable, so small, if and only if every every structure in the class of finite substructure has a finite Ramsey degree. This is a complete combinatorial characterization of small flows, and exactly when the situation is at the previous slide. But what happens if we go to uncountable? We don't know much because people in dynamics do not often care, but we here hopefully do. So, well, if we take an ultra-homogeneous structure, and now I mean ultra-homogeneous again just with respect to finitely generated substructures or finite substructures. Think of power set of omega modulo finite as a nice example where it's good to take the topology that is given by pointwise stabilizers, because you could argue you want a bit larger. Not in all natural structures you do. Then we again get the same conclusion if we have finite Ramsey degree. We do have to go outside of trying to look for such an expansion. We do not know if they exist. This is one of the questions. But we know that in this case the universal minimum flow is going to be small, meaning this is supposed to be size.
What does that
Yes.
formula say?
I will say that this is
Yeah, but what is W?
it's just weight.
And then why take the cardinal? It is a cardinal. The weight is kappa.
Oh yeah, sorry, that's true. I usually write it as the size of the Boolean algebra of Klopen sets. So yes, thank you. You are very correct. That's true. I couldn't find on Jordi's laptop where how to do these lines. I don't know this book how they function. But how about the converse? So we had for countable structures that if we have small flow, small weight, then we also get a finite Ramsey degree, and that makes sense if we are if we are at a countable stage. But what happens here? We do not know yet whether the question is, can we get some interesting infinitary results in there, or the best we can hope for is something finitary. So
what is the weight?
Hmm?
What is the weight? What does that mean?
Oh, the weight is the cardinality of a minimum basis. So these universal minimum flows for groups of automorphisms are going to be zero-dimensional, so they are stone spaces of some Boolean algebras of their Klopen sets. So it's, and well, as I said, the proof for uncountable structures is different than the original paper by Kechristov Todorčević, where they were going to this A star and looking at the quotient description. So we get the description looks the same with a different proof, and we do not know whether we can get the situation backwards. So they used Fraser theory to build the expansion and then take the quotient. We do not know if the result is analogous, whether we can get the homogeneous expansion backwards. So this would be some way of getting large homogeneous expansions, because in general we do not have a way to construct them or to have a control. Well, why? Because in countable case, if we are homogeneous, we are unique. There is only one such structure. Whereas in non-countable case, there is a lot of them. So of course we can be putting more structure, we are keeping homogeneous, but in the end, we definitely do not need to obtain that the restriction to the original language is the original structure. So I was trying to go that way first to build these expansions. I didn't succeed, so I had to find a different proof, but we don't know whether we can use it backwards. Okay, and what was the core of that proof? That was another notion of largeness in topological dynamics, very standard one of synthetic sets. So this is a characterization of minimality in terms of subsets of the group. So flow is minimal if for every point in there and every non-empty open set, the set of those elements of the group that bring M inside of this open neighborhood is synthetic. So this notion of largeness is left synthetic in this case, meaning that there is finite limited translates that cover the whole group. So this is a standard notion from dynamics, but it hasn't been really exploited in the direction of computing universal minimal flows previously. And well, we had a thick set before. Syntheticity is exactly very much joined to thickness. Synthetic sets are exactly those whose complements are not thick. So synthetic sets intersect all thick sets. So we see that if we have every cover by Clopens of the coset space contains a thick set, then we cannot get two disjoint synthetic sets, and that exactly gives us that the universal minimal flow has to be just a singleton, because of course if we have a minimal flow and we have two disjoint open sets, then we will have also two disjoint synthetic sets in the group, and if we don't have them because of all these partitions having a part that is thick, then we are trivial. So from there again this becomes trivial. So as we saw, well, we do not have to have disjoint thick sets, disjoint synthetic sets often, but we do in the discrete case. So a simple argument, but very cute, by Carlson, Heinemann, MacLeod, and Strauss, says that if I have an infinite discrete group, then every synthetic set can be split into further two disjoint synthetic sets. For instance, in the case of integers, synthetic sets are exactly the ones that have bounded gaps. So very simple description. That does not mean that we really know exactly how they look like, but we know there is a lot of them. Well, this is Boolean algebra of Clopens of the universal minimal flow is a witness of power set of Z having a subalgebra of synthetic sets. So all of them are synthetic. Their intersections are synthetic. Of size continuum. It's actually a complete Boolean algebra, and it can be even made invariant under the translation. And this is true for every discrete countable group. So sometimes we have lots of them, but sometimes we don't. And why don't we have a lot of them? Well, in case of groups of automorphisms of ultra-homogeneous structures, this is exactly when we have finite Ramsey degree. So we will have for every A, when we are looking at the coset space G over GA, we will have that A has Ramsey degree T if and only if G can be split into at most T disjoint synthetic sets that are in this coset space. So this is a characterization in synthetic sets. And now, of course, can we do something about this theorem by Carlson and others, and find some combinatorial methods, so theoretic, to to characterize how to obtain disjoint synthetic sets. Okay, so let's go now from discrete to continuous. So the easiest that we actually know something about in the continuous world would be the interval and the group of homeomorphisms that preserve the orientation, and this group is extremely amenable. This is the result by Pestov, and you can derive this from extreme amenability of the group of automorphisms of Q as a linear order. And then from there, you can also get that the universal minimal flow of order-preserving homeomorphisms of the sphere is its natural action on the sphere itself. So these both can be obtained from Q, but surprisingly, this is where we end in this direction. So if we go into two-dimensional sphere, two-dimensional square, we do not know whether it's analogous, we do not know whether if we go into higher dimension there's something different going on. There is now work of Sławek Solecki and his student Aristotelis that is treating these objects as projective Freisel limits. This is what we did for the lilac fan, and there is a hope that we can get some Ramsey properties there and compute universal minimum flows. But these pieces that we built from these triangularizations are not that simple anymore, and it's unclear where we get. So this is something we should know, I assume. And but I will not be talking. This is about continua so much, which is the case in here. But let me move into other settings of continuous structures. So let me bring the analogy in. When we had structures that were discrete, we were looking at ultra-homogeneity with respect to embeddings of finite substructures, and there we had the exact Ramsey property we talked about. If we move into continuous structures, whatever it is, for instance, continua or Banach spaces, then we get a notion of approximate ultra-homogeneity, and often we cannot get exact homogeneity, so this is up to epsilon. And we are looking at approximate Ramsey properties, and as an example there will be the Banach space, the Gurari space, and the group of linear isometries. And we can also turn the arrows backwards, and this is what is natural, for instance, for the interval or the unit sphere. And we get projective ultra-homogeneity and Euler Ramsey properties, so that's what we did for the lilac fan. Or we can add the epsilon in, and then we can apply this to the Paulson simplex. There is work in category theory or from the categorical point of view to put all these things together so we can talk about them together. Obviously, the spirit is the same. The proofs are different, but the proofs even for the discrete case of Ramsey theorems are different, so this is not really... There is nice attempts to make it into one language. And in the approximate world, we get the same analogy between approximate Ramsey property now and extreme amenability of groups of isometries of these continuous structures. I don't want to go into continuous logic, so I'll just give examples. In Banach spaces, we have the Gurari space, universal approximately homogeneous separable Banach space, and we have the approximate Ramsey property for finite dimensional norm spaces. Or for simplices, we get Ramsey property when we take the Paulson simplex and we choose one of its extreme points and take the group of affine homeomorphisms. We get this extremely amenable, and on the combinatory cell, approximate Ramsey property of finite dimensional simplices. This is being written up in the common paper with Jordi Lopez, Abad, Martino Lupini, and Brice Mombo. Okay, so let me introduce these objects just so that we have an idea what we are talking about. So Gurari space is a separable Banach space. It is universal for all finite dimensional Banach spaces. And it's approximately ultra-homogeneous. There is no exactly ultra-homogeneous Banach space that is separable for finite dimensional embeddings, but approximate homogeneity we can get. Well, what does it mean? Now we start again with a linear isometry, but what we get is a linear isometry that on the original space can move by epsilon. Or we can also think of it as we extend to something that is not exactly isometry, it's epsilon isometry, and it stays the same. These are the two equivalent definitions. And Lusky proved that this is a unique thing again. So similarly as for countable ultra-homogeneous structures, here we get also unicity. And there is a simple proof now by metric Freisel theory. So we had these Freisel structures in the countable discrete case. Now there is metric Freisel theory for these for continuous structures, and then the unicity comes out for free from this general viewpoint. And the group of linear isometry is very similar to the discrete structures, but we have to count in epsilon, so we start with some finite dimensional subspace, some error, and we are looking at almost stabilizers, so linear isometries that move a little bit away from the identity. And analogically to the group of isometries of the Eurizon space, separable Eurizon space, this group is universal Polish group, and but Itaj-Benjakov used a modification of the Katětov construction that Katětov used for Eurizon space. So this is what we are talking about. And we are proving that the group of linear isometries has the approximate Ramsey property, and it is enough to prove, to build the Gurari space from finite dimensional L infinity n spaces. So that's just finite sequences of real numbers with the maximum norm, supremum norm. So we can build Gurari space as a direct limit of these guys and a completion of that. Of course, this is not just adding one coordinate, there is bonding maps that make it universal and homogeneous. And we start exactly the same as in the finite Ramsey theorem, so this is nice combinatorial statement. Well, before that we set K instead of D, but modulo the latter is the same, so we take number of colors. Now we have to have an error, and the solution will be changing depending on the error, so there exists again some large dimension such that when we color all embeddings from the small dimension into the large one by R many colors, then there is an embedding from the medium size space into the large one, and one color such that we are almost monochromatic, meaning maybe we will not be exactly in the color, but somewhere around there the color will appear. So this is the best we can hope for. The exact result is not true, so and this is enough to prove extreme amenability, because again we have approximate ultra-homogeneity, so we can make errors. And what we are using is the dual Ramsey theorem, so it's very combinatorial in nature. So it's the picture is basically there, but we can also copy it here. We start with a small and larger set, and we are looking for a large solution for a given number of colors, such that when we color all partitions from the large set into k many pieces, there exists a partition into m many pieces, such that all further partitions have the same color. So this is an exact statement, and by discretization from there we get this approximate statement for embeddings of Banach spaces. This is a very powerful statement in Ramsey theory and way more difficult to prove than the direct one, even though in categorical theoretic language we just turn arrows to give the statement. And from the Banach spaces we also get a result for the Eurizon space. So Pestov proved by a concentration of measure that the group of isometries of the Eurizon space, so this is the universal homogeneous object for finite metric spaces, is extremely amenable. And we proved directly, he proved that this is equivalent to finite metric spaces having the approximate Ramsey property, but we have a combinatorial proof of that property, and from there we can deduce extreme amenability. There is also another way to prove extreme amenability, and then this is because here we do actually have real ultra-homogeneity, meaning that if we map one metric space isometrically to the other, there is an exact isometry, so there is no errors. And Escher will prove this Ramsey property for finite linear ordered metric spaces, and we can take its countable limit, the rational Eurizon space, and then completion of that is the big one. So there is multiple ways these days. And now let's switch the arrows, move them backwards, and we go into simplices. So well, we first have a direct definition of the Poisson simplex. It's metrizable. It's very analogous to Gurari space, but for simplices. Contains every metrizable simplex as its face, and it is homogeneous for its faces. So if I take any two faces with the same dimension, then we have an affine homeomorphism bringing one to the other. And we get again unicity up to affine homeomorphism, which is the maps we are considering in this category. And Paulson built this to show that the set of extreme points is dense. And for instance, this appears all around. If we take just a shift, the Bernoulli shift, then the Paulson simplex is the space of invariant probability measures. So it's an object that it was not cooked up just to have an example. So now we have the Ramsey property for pointed simplices. So if we can move around the extreme points, we do not have Ramsey property, but if we fix that, so this is similar as rigidification in the discrete setting. So we are looking at continuous affine surjections preserving one extreme point. Well, we can always think of these simplices as just positive parts of balls of L1s to n, right? So we get some standard representation, and we have exactly the same theorem as for L infinity n's, but now with reverse arrows, and instead of finite dimensional 1s spaces, we get finite dimensional simplices. So modulo an error, we get monochromaticity in here. And now from there we derive that if we take the group of affine homeomorphisms of the Paulson simplex fixing a certain extreme point, then this is going to be an extremely amenable group. So again, from the approximate Ramsey property. But here we also have a description of the universal minimum flow in the same way as we had for countable structures. So we can describe it as taking the homeomorphism group, the extended structure, which is extended by this one constant, fixing one point, extreme point, and taking the quotient and a completion. And this is going to be the Paulson simplex because the group of affine homeomorphism acts transitively on extreme points, and they are dense. So we get a natural action. But it took a while to prove it. And let's get to the last problem. Well, it first appeared in a paper by Pestev, who asked whether the universal minimum flow of the group of homeomorphisms of the Hilbert cube is its natural action. And then Uspensky proved that it is not, that the action on the universal minimum flow cannot be 3 homogeneous, meaning that we cannot be able to move every 3 points to arbitrary other 3 points. Then Gutmann improved that it cannot be even 1 homogeneous. So it is not, but we have some results about some subgroups. Well, as every infinite dimensional simplex, this Paulson simplex is homeomorphic to Q. So there is some convex structure that we can put on the Paulson simplex, on the Hilbert cube to make the homeomorphism group that preserves this this affine structure to be to have the universal minimum flow, just the natural action on itself. And if we take the natural convex structure, we get even a smaller group. So we get a group that is just 2 to n times S infinity. And from there, we get combining the result of Glasner and Weiss, and just the compact group that the universal minimum flow of affine homeomorphisms of the Hilbert cube with its natural convex structure is this guy. So maybe putting some convex structures, all of them would be the universal minimum flow, but this is still in a baby stage. Okay. Thank you very much.
Very much. Any questions, comments? Yes.
So maybe I should mention, since you mentioned this question of mine, if anybody looks up that question in my paper, they should also be aware of your observation that you made in Norwich, that it's wrong. In the paper, I neglected to say that things should be rigid.
Yeah, but I was only presenting things in the rigid.
About rigid, so everything is fine. But if you read my paper, take the rigid from the talk and stick it in the paper.
Any other comment or question? Well then, let's thank the speaker again.